Hmm. Why is my video not working? All right, sorry about that, class. Um, I was streaming, but for some reason the video wasn't coming up, so I had to restart some stuff. I'm going to wait a little bit longer until I get started. I'll be right back. Hello. Hello. Buenos días. Yo aprendo los otros verbos en español. Por ejemplo, hacer y hacer y querer y what was the other one? The other one was now it's gonna bother me. Now I have to look it up. What was the other one I learned? Ah, poder. So I'm trying to get all of the irregular verbs. Oh, yo comprendo tener. Sí, sí. Yo tengo, tú tienes, él tiene, nosotros tenemos. Sí. Ellos, ellos tienen. No. Okay. I'm going to go ahead and get started on something other than Spanish. ¿Verdad? I should ask you this. ¿Ustedes quieren aprender la física? ¿Sí o no? Okay, I'm going to assume that the answer to that question was C, and I will get started. All right, so we are almost done with forces. One of the things I have to say about physics, the IB physics class, is that we cover a lot of different topics in not quite as much depth as the AP Physics. So AP Physics 1 goes a lot slower than this class, but we do more problems. So this is kind of just an overview of forces. This is going to be our last forces lesson, and then next lesson we're going to go start talking about energy. Okay, so let's go ahead and get started. Today we're going to talk about interacting systems. And why is that so blurry? I do not understand. That drives me nuts. It doesn't focus sometimes. Interacting systems. Okay. So the classic system that we're going to talk about today is something called an Atwood machine. ATTWOOD, Atwood machine. And it's a good teaching tool to understand how to solve this kind of problem. Okay. So what we have is a pulley. So I will represent the pulley as a circle with a dot. Okay. And then we have two masses. So I'll call this M1, and I will call this M2. Okay. And the two masses are connected by a rope that goes over the pulley. Okay. And that's an Atwood machine. So let's assume that M1 is greater than M2. So what that means is that M1 is going to fall and M2 is going to rise. Okay. We are also going to assume a frictionless pulley. Frictionless, massless pulley. So what that means, a frictionless, massless pulley means that the pulley itself has no influence on the motion of the masses. If the pulley had a mass, then we would have to worry about its inertia. It takes energy to get a pulley that is heavy to start turning. So we're going to neglect that. We're just going to assume it's a frictionless, massless pulley. And furthermore, we are going to assume a massless rope. Connects the two masses, M1 and M2. Okay. If you have a massless rope, that means that the tension is the same throughout. Okay. So in other words, the way that ropes work. By the way, the force from a rope is called tension. Tension is the force from a rope, and I will denote a tension by F sub T for force of tension. And the way that tensions work is that if you have a massless rope, let's say that this rope is pulling up with, I don't know, 5 newtons of tension or something, then that tension gets transmitted through the rope, and this one is going to get pulled up with 5 newtons also. So the tension that one end of the rope is pulling at is the exact same as the tension that's pulling on the other end of the rope. Okay? So that's the way it works. So what we would like to know is, first of all, what is the acceleration of the system? Okay? And secondly, what is the tension in the rope? Okay? Now, one comment about the acceleration. There is really only one acceleration in this system, okay? Because, as we said, M1 is going to be falling and M2 is going to be rising, but they're going to have the same acceleration. Why? Because they're connected by a taut rope, okay? They're connected by a taut rope. So what if M1 falls 1 meter in 1 second? Then that means that M2 rose 1 meter in 1 second. So they're linked by this rope. So if one falls a certain amount in a certain amount of time, then the other one rises that same amount in the same amount of time. Okay? So that means basically that their position time graphs are the same, which means that their velocity time graphs are the same and their acceleration time graphs are the same. So they have the same acceleration. A1 equals A2 when the rope is taut. Okay? So that's important to remember, that the rope has to be taut for that to be true. And the tension, same throughout. The rope. Okay? So these are the things that we need to solve this problem. Okay, so how do we solve these interacting systems problems? Well, what we want to do is we want to assume a positive sense for the motion. Okay? Assume a positive sense for the motion. So because M1 is greater than M2, I know that M1 is going to fall and M2 is going to rise. All right? So I'm going to choose the positive sense of rotation to be the counterclockwise sense. Okay, so if the pulley is spinning counterclockwise, that's the positive direction. So this makes things a little bit confusing, because downward is going to be positive for M1, okay, but upward is going to be positive for M2. You see how that works? Because I've chosen this sense to be positive, all right? So let's go ahead and choose some specific numbers. So I'm going to draw an Atwood machine. Let's say that this is 5 kilograms. Okay. And let's say that this is 1 kilogram. All right, and they're connected by this rope that goes over the top. And I'm going to choose this to be the positive sense. Okay? So if I did a free body diagram on the 5 kilogram block, it is going to have a weight force going down, all right, which would be M times G, or 50 newtons. 50 newtons going down. And the thing that is slowing the 5 kilogram mass down is the rope that's pulling up on it. So it's going to have the force of tension going up. Okay? If we look at the 1 kilogram mass, it has tension pulling it up and weight force holding it back. Okay, the weight force on this 1 kilogram mass is going to be m times g, 1 times 10, 10 newtons. Okay, so we call this an interacting system because there are two masses. All right. And by the way, the pulley is held fixed, so the pulley is not moving up or down. All right, now a couple of things. Because the tension is the same throughout the rope, this force has to equal that force in size. Okay. Notice how for the 5 kilogram mass, I have drawn the 50 Newton arrow to be longer than tension. Why is that? Because the 5 kilogram is heavier than the 1 kilogram, so I know that this 5 kilogram mass is going to accelerate downward. If the 5 kilogram mass accelerates downward, then its downward forces had better be bigger than the upward forces. Okay? Just the opposite is true for the 1 kilogram mass. The 1 kilogram mass is going to get lifted by the rope. Okay? And so the upward forces had better be bigger than the downward forces. So I've reflected that in my drawing here. Okay? So what we're going to do is we're going to do Newton's second law for each mass. So we're going to do net force equals ma for the 5 kilogram mass and for the 1 kilogram mass. Okay. All right. So doing net force equals ma for the 5 kilogram mass, we have 50 newtons going down and we have tension going up. But remember, because of the positive sense I've chosen, downward is positive for this heavier mass. Okay? So the net force is actually going to be 50 downward forces minus upward forces. So the net force is going to be 50 minus F sub t. Okay? 50 minus F sub t. The net force for the 1 kilogram mass is going to be, and for this mass on the right, upward is positive because the positive, we have a positive sense, which is this sense, okay? So the positive force for this one is going to be F sub t because it's going upward, and the 10 newtons downward is going to be negative. So we have F sub t minus 10 is the net force for that. Okay? And that equals ma. So for the 5 kilogram mass, this is going to be 5a. And for the 1 kilogram mass, this is going to be 1a. All right? Couple of things to remember. The two tensions are the same, so I don't have to have an F sub T5 and an F sub T1 because it's the same rope, so therefore the same tension. Second thing to note is that even though these are different masses, their accelerations are the same because they're connected by the taut rope. So if the 5 kilogram drops 1 meter, the other one rises 1 meter. Okay? So this is what we would call a system of equations for F sub t, the tension, and the acceleration, because we have two equations for two variables. So how do we solve this? It's actually really easy to solve. What we want to do is we want to add the two equations. Okay? Now if we add the two equations on the right-hand side, we have 5a plus 1a. So that is 6a. On the left-hand side, notice how we have minus f sub t and we have plus f sub t. So when we add those, they cancel out. Those cancel each other out. And then we have 50 minus 10. 50 minus 10 is 40. Okay? So then we can divide both sides by 6, and we would get, what, 6.6 meters per second squared is our acceleration. So we're halfway there. Okay? Once we have the acceleration, we can plug that back into either one of these two equations and solve for the tension. Okay? So I'm going to plug the acceleration back into this equation right here. So I have f sub t minus 10 equals 1 times 6.6. So that means that the tension in the rope, adding the 10 to the other side, f sub t equals 16.6 newtons. Okay? So, if we just talk about, now if we had a good way to double check that you have the right answer is to take this 6.6 and also plug it into the other equation and make sure that you get the same tension. I'm confident in my math skills, so I'm not going to do that. But if you're not, you can plug it back into both equations. Actually, why don't we just do that? We would have 50 minus f sub t equals 5 times a. So 5 times 6.6 is going to be 33.3. Okay, and then I subtract 33.3 from both sides, and I add f sub t to both sides, and I get f sub t equals 16.6. All right, so I'm confident that I have the right answer. Another comment I wanted to make is that notice how the tension is smaller than 50 newtons. So that's going to allow the 5 kilogram mass to accelerate downward. And the 16.6 is bigger than 10, so that's going to allow the 1 kilogram to accelerate upward. So it all works out just as I said. There are other examples that are sort of analogous to this, okay? So the next example I want to do is, what if we had a table? So here's the legs of the table. Oh, excuse me, una mesa. Esta es una mesa. This is a table. Here is the ground. I don't know how to say ground. Here is a pulley that is on the edge of the table. Here is a mass that is sitting on the table. Here is another mass that is not sitting on the table. So we have a rope connecting them. Okay. And let's say that this is, again, a 5 kilogram mass. What is ground? I feel like one of you is going to tell me a bad word is the ground, so I'm looking it up myself. That actually sounds completely like a bad word to me in Spanish. I won't say it. Oh, los dos son opciones. Okay, so I can use both of those. Okay, I have confirmation. So, anyways, we are going to have that there's a coefficient of friction, okay? We'll say that the coefficient of kinetic friction is 0.2, okay? And so we're going to assume that the 1 kilogram mass is heavy enough to pull the 5 kilogram mass across the table, okay? So we're going to call this sense the positive direction, all right? So let me draw a free body diagram of the 5 kilogram mass. So free body diagram is just a picture of the forces, okay? The 5 kilogram mass is going to have 50 newtons going downward, okay? It's going to have the normal force going upward. That's the normal force from la mesa. It's going to have friction going to the left. That's going to be kinetic friction. Why? Because the 5 kilogram block is sliding to the right. And it's going to have the force of tension pulling it to the right. Notice how I have force of tension is bigger than kinetic friction, because if it wasn't, then the 5 kilogram block wouldn't actually get pulled to the right. Okay? Now, this 5 kilogram block is moving left to right. It's not moving up and down. So that means that the up and down forces have to balance. So those balance. So that means that the normal force is 50 newtons. Once we know the normal force, we can then calculate kinetic friction. Kinetic friction is going to be mu sub k times the normal force. So we have coefficient of kinetic friction is 0.2, normal force is, I'm going to make this, I'm going to edit my coefficient of kinetic friction, okay? I gotta be, I'm going to make it 0.1 instead. Sometimes, so I had chosen a coefficient of kinetic friction that was too large so that this block wouldn't actually slide. So I won't do that to you. I will always, choose my numbers so that there are no contradictions, okay? So that has to be 0.1 in order to allow the block to slide. So we have 0.1 times the normal force, which is 50. So that says that kinetic friction is 5 newtons. So this is 5 newtons. All right. Then, if we look at the 1 kilogram, it has a weight force of 10 newtons going down, and it has a tension holding it back. Remember, these two tensions have to be equal. So I'll put double slashes to indicate that they're equal. All right? So what is the positive direction for the 5 kilogram mass? Well, the positive direction for the 5 kilogram mass is to the right, okay? Because it's moving to the right. The positive direction for the 1 kilogram mass is downward because it's moving downward. So the way that you want to solve these interacting system problems is you want to I spaced out for a second. what you want to do is you want to just have the positive direction be the direction in which that mass is going to move. When it gets tricky is if you don't know which direction it's going to move in. But this is your first physics class, so I'm always going to make it obvious which direction the masses are going to move. Okay? All right, so now we're going to do net force equals ma for the 5 kilogram mass and the 1 kilogram mass. All right? So for the 5 kilogram mass, the positive direction is rightward. So the net force is going to be right forces minus left forces. So F sub t minus 5, because friction was 5 newtons. And that equals ma. For the 1 kilogram mass, the net force is, remember, downward is positive for the 1 kilogram mass, so 10 minus tension. 10 minus tension equals 1a. All right? How do we solve this system? You want to add the two equations together, which will automatically cancel the tensions. That happens every single time with these problems. Okay? So that's why you always want to add together. And then we get 10 minus 5. So that's going to give us 5 is the net force. And then adding these two together, we get we are going to get 6a. Dividing both sides by 6 gives us 5/6, which is what? 0.83 meters per second squared is the acceleration, which I would then plug in to get the tension. So plugging that into that bottom equation there is going to give me 10 minus F sub t equals 0.83. So that means the tension is 9.16 newtons. Okay? We're going to do one more example just to make sure that y'all understand. All right, so the last example I want to do is we have una mesa y un piso. We are going to have trace masses. I don't know how you would say masses in Spanish. We're going to have 2 ropes. Okay. So if you have 2 ropes, there are going to be 2 tensions. So it's a unique tension per rope. All right, because this mass has a rope on one side and a rope on the other side, that doesn't mean there's just one tension. It's one tension per rope. Okay? We're going to say that the table is frictionless. Okay? We are going to have, the masses are going to be 3 kilograms, 2 kilograms, and 1 kilogram. Okay? So, based on this, I hope it is obvious to you guys that this system is going to rotate in that sense. Okay, because 3 kilograms is heavier than 1 kilogram. So that's going to be the positive sense. So notice how the 3 kilogram has a 30 Newton weight force going down, and it has a tension, which I'll call F sub T1. So this is rope 1, holding it back. If we look at the 1 kilogram mass, it has the tension from the second rope, so I'll call that F sub T2, pulling it up, and it has 10 Newton weight force holding it back. If we look at the 2 kilogram mass, I'm going to draw its free body diagram over here. It has 20 Newtons going down. It has a normal force going up, which is also going to be 20 Newtons. It has the left rope pulling it to the left, and it has the right rope, the second rope, pulling it to the right. Okay? So there you have it. In this problem, the vertical forces on this mass do not really matter. Why is that? It's because this 2 kilogram mass is moving left to right. It's not moving up and down. So the vertical forces have no bearing on how it's going to move. Okay? All right, so we're going to do this again with Newton's second law. Net force equals ma for all 3 masses. So we have the 3 kilogram mass, we have the 2 kilogram mass, and we have the 1 kilogram mass. Okay? And all 3 are going to have the same acceleration because they all are connected by taut ropes. Okay, so if the 3 kilogram mass falls 1 meter, the 2 kilogram mass is going to move to the left 1 meter, and the 1 kilogram mass is going to rise 1 meter. So they all travel the same distance in the same amount of time. So what is the net force on the 3 kilogram mass? Well, downward is positive for this mass, so it would be 30 minus the first tension. So that equals 3a. If we look at the 2 kilogram mass, it has tension 1 pulling it to the left, which is the positive direction for it, and tension 2 pulling it to the right, which is the negative direction for it. So F of T1 minus F of T2. Keep in mind that normal force and weight play no role in this problem because the 2 kilogram mass moves left and right. So these two subtracted equals 2a. For the 1 kilogram mass, it has tension pulling it up, tension from the second rope, and it has the 10 Newton weight force holding it back. All right? So one of the things I wanted to point out is neither of the dangling masses has a normal force acting on it. The only time you have a normal force is if you are in contact with a surface. Okay? If this 1 kilogram mass was resting on the ground, in that case, you would have a normal force, but it's not resting on the ground. The 2 kilogram mass is resting on a surface, so it does have normal force. So the way to solve this is to add the equations together. And one of the things we notice is that we have Ft1 and we have minus Ft1. So when I add, those two cancel. I have Ft2 and I have minus Ft2. So when I add, those two cancel. So when I add the left-hand sides together, I get 30 minus 10 is 20. When I add the right-hand sides, I have 3a plus 2a plus 1a. That is 6a. All right. Then I divide both sides by 6, and I get that the acceleration is 3.3 meters per second squared. Okay. Then if I want the tensions, I can plug them in to the equations. I would plug them into the top and the bottom equation. So for this 3 kilogram mass, I have 30 minus FT1 equals 3 times 3.3. And then for the other one, I have FT2 minus 10 equals 1 times 3.3. So that says that FT2, the second tension, is 13.3 newtons. And the other tension from rope 1 is going to be, it looks like, what, 20? 3 times 3.3 is 10. Yeah. All right. So there you have it. That's my lesson for today. We're going to switch over to the Zoom room at this time.